So let's look at some of these work problems now on resolving forces and talk about the trigonometry that's involved with it. These work problems, you'll see they work through in the textbook as well, but they're probably going to do it in a slightly different way, and that's good because you can see their way and my way, and then hopefully one of them will click. And you've also had some information from Omar, so you're getting this from a few different points of view. Resolve the force vector of 50 newtons at an angle of 35 degrees to the horizontal into its horizontal and vertical components. If we go back and look at this drill for a second, this answer, x, 8.23, would actually be a vertical component of this 12.8 Newton force. So what we're actually saying is, if we go back to this drill question, if this 12.8 represented a force of 12.8 newtons going in that direction, we found the effect of that force in the vertical direction is 8.23 newtons. And common sense would tell us, wouldn't it, that if this was somebody pulling on a rope with a force of 12.8 newtons that way, then I'd expect not quite 12.8 newtons to be going vertically, which is the case, about 8.23 newtons. So we can use this idea of trigonometry to resolve forces into its horizontal and vertical components. If I was looking at this problem, I would draw it 50 newtons at an angle of 35 degrees to the horizontal. Draw a force of 50 newtons at an angle of 35 degrees to the horizontal. So the first point about drawing is that I would draw that. I would not draw this and then measure that as 35 degrees. I would not draw that and measure that as 35 degrees. I know because of convention that it's like that. So the first thing to do is sort out conventions. If I extend these dotted lines like this, I've actually got these four quadrants. So it's like a graph with this as being the zero, the origin, and therefore all angles are measured from this positive x-axis anti-clockwise. So I know that this 35 degrees, because of convention, 35 degrees is measured anti-clockwise from the positive x-axis. Okay, that's the convention. There has to be a convention so that when somebody says measure 35 degrees for the force, you know where it's supposed to go, and that's the convention we use. Okay? So I've drawn it. Now I want to resolve it into its horizontal and its vertical components. That means I need to find the effect of this force vertically and horizontally. It's vertical and horizontal components. So I'd label them FV and FH, and I'd use trigonometry to do it. I'd actually imagine this force line is shifted over here, and that's my vertical component. It's actually acting at this point in the middle, 0, but to calculate it, I just make it form the missing side of my right angle triangle. Because of this convention, 35 degrees measured anti-clockwise, so I know it's going that way. Okay. It is a good question though, Cameron, actually, because another convention might well have been used here, which is to say that we might say up forces is positive, so therefore down forces are negative. And that convention does change. Sometimes it's convenient to have the down as your positive because you're talking about lots of down forces all the time. Sometimes convenient to use up forces positive. So that changes depending on the situation, but this convention never changes. It's always the same for angles. So thanks for that, Cameron. Right, we've got our right angle triangle now. I might decide actually to do a side diagram, because this is starting to look a bit complicated now. So just so I'm not going to make any mistakes, let's just draw my little triangle out to the side here. I know that's 50. I know that's 35. I know this, and I want to find this, which is the vertical, and this, which is the horizontal. So what do I do now, Daniel? Okay. Yeah. Yeah. Right. Times by the. So in fact, it turns out to be that the vertical component of the force is 50 newtons times the sine of 35. Okay. Horizontal component, somewhere in the middle, would be? Well, what would the calculation be? Yeah, 50 times the cosine of 35 degrees because of the SOHCAHTOA. In this case, F horizontal is the adjacent, so we use cosine. And then we do that in the calculator. So if you do that, please, just to check you know the calculator process. 41. Okay, newtons to two significant figures, which is appropriate. And this one would be?
Oh, no, that's the bottom one.
Is it?
And then the vertical 28.6, so it is
Right.
29.
A case of where appropriate accuracy is here, because the sign will give us lots of significant figures, so we need to round to an appropriate number. Agreement there? Resolve the displacement vector of 40 meters at an angle of 120 degrees into horizontal and vertical components. So let's look at this one. Let's first of all start off with our guidelines almost. So this is the origin. All angles are going to be measured from the positive x-axis anti-clockwise. So that's how I'm going to measure angles. Now I want to draw this thing out. Resolve the displacement vector of 40 meters at an angle of 120 into its horizontal and vertical components. So this time I go around 120 degrees. So 90, 120 is around about here somewhere. So that length's 40 meters. And this angle is 120 degrees. So again, following the convention and know exactly where that is. And this is the sort of thing I would do measuring bearings for displacements. And they'd normally actually be measured from north. But so that's a different convention that's used for ship yachting and stuff like that. Measurements are always measured from north. But here we're sticking to this positive x-axis. So now I've got to again find the vertical and horizontal components. So the vertical will be this one, and the horizontal will be this one. So again, I would shift the vertical across to over here, so it sort of forms a right angle triangle. So I might draw it to an aside now to find it. So I'm after this, which is the displacement, S for displacement, so that's the vertical component, that's the horizontal. This is 40, but what's this angle? Yep, 60, yeah. So this is an example of where you're not always given directly the angle you need. You need to draw it and then see what your right angle triangle looks like and which is the angle we know. In that case, this is 60, not 120. You see that? Now it's the same, okay? Just finish this off for me, please. Find us the vertical and horizontal displacements. So now we've got the solutions, we need to put these back. So we now find that if we finish this problem off, we've got 40 meters displacement going this way, which has then got a horizontal of 20 meters and a vertical of 35 meters. There might be a case now, if you weren't drawing this, to say, let's talk about up direction being positive and right direction being positive. So if that's the convention we're using, then we would state that to the side here. So we're going to talk up being positive and right being positive. Then that means this is a negative 20 meters this way and a positive 35 upwards. But it would all depend on the convention. Pardon? Well, actually, it's 40 meters, yes, but it's got a positive vertical and a negative horizontal component to it. So that's the way you sort of talk about that. What you're not sure of there, Cameron? Let's look at this one. We've got a force of 5 newtons inclined at an angle of 45 degrees to a second force of 8 newtons, both forces acting at a point. Calculate the magnitude of the resultant of these two forces and the direction of the resultant with respect to the 8 Newton force. So what we do is we draw the 8 Newton force as being our horizontal, because we're after what the resultant of that, of these two forces, is with respect to that. So that's going to be our start point. So now we draw the 5 Newton forces inclined at an angle of 45 degrees to that. So we draw a second force of 5 newtons at an angle of 45 degrees. And what we're after is the magnitude of the resultant of these two forces and the direction of the resultant with respect to the 8 Newton force. So you might have done this sort of thing, I don't know, with Omal. I draw a line here parallel to that one and a line here parallel to that one. We form what's called a parallelogram of forces. And then the resultant will be this line. So we're after that. And we're after the size of this resultant force. So let's call that F for, well, actually let's call it R for resultant. And we're also after this angle here, theta. The angle of this resultant with respect to the 8 Newton force, theta. What we're going to do is try and find this resultant by calculation, using the idea that we can split this force, the 8 Newton force, into its horizontal and vertical components, and the 5 Newton force into its horizontal and vertical components. So the basic principle is that if I have a force, one going this way and one going this way, say, and I want to add them together, what I do is I find out what the horizontal component of this is. What's going on? Okay, I'll use blue. So imagine we've got this, the horizontal bit of this. So we find out the horizontal component of the first force and the vertical component of the first force. We find the horizontal component of the second force and the vertical component of the second force, which will be going down this way. And then, to get the resultant, we add this one and this one. So we take this line a shame, it won't let me do it. We take this line and this line, so that's this line here and this line, and add them together to get the total horizontal component. We take this one and this one and add them together, so one will be positive, one will be negative, and add them together, and by calculation, and then we end up with the resultant of those two forces. That's the plan, which might be a very convenient way of doing it. By all means do that. So what we're going to do is take the 8 Newton force and find the horizontal component and the vertical component. So if we look at just the 8 Newton force, this is actually quite straightforward because it's only got a horizontal component. The horizontal component is 8 newtons. The vertical component is 0. There's no components of this 8 Newton force acting upwards or downwards. Okay? Then we take the 5 Newton force and do the same thing. What's the horizontal component of the 5 Newton force? So now we've got a triangle. If we take this triangle, it's 5 newtons acting at 45 degrees. So 5 newtons acting at 45 degrees. And we want this, the horizontal component. Let me just draw that a little bit better. 5 newtons acting at 45 degrees. And we're after this horizontal component and the vertical component. So what's the horizontal going to be? What's the calculation? This is 5, remember? It's this one, so it's cos, yep, cosine adjacent, so it's 5 times the cosine of 45, and the vertical is, right, 5 times the sine of 45. And then we work out what they are, and we can then add up what the total horizontal is and the total vertical is. So if I just pause a sec, you can get that up to that point, please. Do with this now. We've got, therefore, we can say that the total horizontal component equals, the first force, the horizontal component, is 8 newtons plus 3.5 newtons, which is 11.5 newtons. So we've got the total horizontal component of this force. The total vertical component is 0 plus 3.5, so that equals 3.5 newtons. So we add up the total vertical and horizontal components, and it sounds like you might put this in a table, so you just add them all up. What are all the horizontal bits? What are all the vertical bits? So you can apply this principle to any number of these forces. And then we draw the thing. So we've got 11.5 newtons and 3.5 newtons. And we're after the resultant. So if I just form the rectangle and then I can draw this line in, that's the size of the resultant, R. So this is 3.5 because the other one's 3.5, and we've got ourselves a little right angle triangle here. And we're after, if you remember the original problem, we're after theta, the angle, and we're after R. So now we've got Pythagoras that we've looked at to find R. So we use Pythagoras to find R. So r is alongside, so r equals the square root of the 11.5 squared plus 3.5 squared. And that will give us a size of the resultant of the force, which is, Jack? Exactly. Right, so 12 newtons to two significant figures. And theta, actually now we've got all three sides. We've got the resultant and the opposite and the adjacent. So in theory we could use any of the ratios, sine, cosine or tangent. But it's good practice to use the actual, rather than the resultant, use these two. So we use the opposite and the adjacent, which is to do with the tangent. So we use that. Tangent of theta equals the opposite, which is 3.5 over 11.5. So therefore theta is the inverse tan of that. I've not talked about the inverse tan, but you're happy with that function on the calculator? The angle whose tangent is 3.5 over 11.5. So theta actually equals the inverse tan of 3.5 over 11.5. And I would use the fraction button to do that on the calculator. So I'd go inverse tan and then use the fraction button and then 3.5 over 11.5. And it would give me the angle, which is 16.9. Nearest degree, 70 degrees for two significant figures. I wouldn't generally write parts of a degree. The nearest degree is good enough. Yeah, we know tangent. We use tangent because we know the opposite and the adjacent. Yeah. Right, I'll just pause there. Yeah.